Okay, everyone, let's take a look at Unit C, Unit C3, panel methods. Okay, so Unit C3, panel methods, I'm going to first introduce you source panel method. Now, source panel method is a very fundamental panel method, however, it's really not practical. So we are going to understand how the panel method works by using source panel. However, for practical purposes, we are going to use the vortex panel instead. So after we cover source panel and vortex panel methods, I'm going to demonstrate you how to use the software that you are going to use for your course project. Okay, let's move on. Alright, so Unit C3, page 1. I want to begin with this page. Well, this page illustrates you the three fundamentally very different approaches for aerodynamics. Aerodynamics is a very, very large field. So one person really cannot cover everything. Okay. And roughly speaking, we have three fundamentally very different approaches in aerodynamic problem solutions. Now, Aero1 covers mainly this one, pure theory. So that's why we are going to focus on fundamental equations, governing equations to begin with. And then we are trying to develop ideal flow theory, which is essentially pure theory based. So we are using 100% mathematical approach to trying to solve the problem. Of course, the shortcoming for that is that we are going to apply lots of assumptions, and more assumptions, simplifying equations to solve it. So sometimes the results based on the ideal flow is not necessarily the same as real flow field. Okay, so that's the shortcoming for this approach. However, this one serves the foundation for the other two. Okay. Obviously, this one is a pure experiment. If you are in aerotrack students, you are going to take experimental aerodynamics class later on. Of course, that is typically using wind tunnel testing to find out flow field properties and problem solutions. But this one is basically built upon this pure theory Aero1. This one is a completely very different approach, computational fluid dynamics CFD, which I do offer the class occasionally. So if you're interested, you can take this one. But this one is 100% computer simulation. So essentially you are using computer trying to solve the governing equation. So these two are fundamentally very different. However, those two are built upon Aero1, which is this class. Okay, now so panel methods essentially belong to here. It's an extended approach of pure theory. So let's be careful before we begin. I'm going to write it down. Since panel methods are built upon assumptions. So it belongs to this pure theory. Okay. And then also later on we are going to talk about thin airfoil theory. Okay. So those are theoretical schemes. Theoretical problem solution approaches. This is basically simplified equations based on assumptions. Usually steady state. Oftentimes viscosity is ignored. And then of course we just ignore body force, gravity. And oftentimes density change is ignored. And in order to simplify your mathematics, we oftentimes ignore vorticity. Rotational really means that the vorticity of the flow field is this actually massively simplifies the mathematical analysis here. So oftentimes we kind of tend to forget about when we use the engineering tools such as panel methods and therefore theory. Please do not forget about those assumptions already built into the analysis. So the results you get may not necessarily be accurate result because simply you are ignoring some or all of those phenomena of the flow field. So if your results are not satisfactory results, of course you're going to put those assumptions back into it. Okay, let's include rotational effects. Let's include the change of density. Let's include the gravity. Let's include the viscosity. Let's just do not even assume steady state. So you can actually put those assumptions back on it, layer by layer, if necessary. You can build more accurate analysis later on. But panel methods and therefore theory, because this is pure theory, even though the analysis is based upon those assumptions, the analysis is really fundamental analysis step, what you need. So later on you can add those things back on. Each one of those assumptions which you ignore, you can model and then add on to the results that you get from panel method and Singh-Elfman theory. Okay, so let's move on to next page, page 2. Now, I'm not going to cover the mathematical details of panel method. The reason here is because we are going to use the software already developed by someone else, and then it's not our scope of this class to find out how to code the source panel or vortex panel. Let's focus on what is it and how does that model is being built, and how can we use the software to analyze. Okay, so I'm going to focus on those things. So let me just take a look at source panel method first. Okay, let's begin with a point source we introduced in the previous units. Okay, point source is at the location you are going to have velocity comes up. This is called point source. Of course, we looked at it. We even superimposed this point source against uniform flow, establishing the flow over some kind of two-dimensional shaped body. Okay, so we are going to extend this into line of source. This is essentially 2D analysis. So suppose if this point source is going to be sitting side by side, in fact, you're going to consider a line created by this point source, series of point sources. Okay. So this is line of source. Since this line is made up by point source in the series, of course this is going to create the velocity or flow field just like this. Okay. Then I'm going to extend one more step. Let's call this panel of source. Here we go. It's a 3D concept. So that's what you're seeing here. Okay. So this is a three-dimensional panel of the source, or called source sheet. So this is a three-dimensional panel. Each one of them is probably flat plate. Okay, flat plate, flat plate. So this is a one panel, second panel, third, fourth, fifth, you know, it's a series of panels to represent curved surface. Okay, so this is called source sheet and source panel. Okay, so once this kind of thing is placed in the flow field, since this is made up by source, you are going to create the flow. If you create the flow, depending on the magnitude of each panel, you are going to create a different value of flow out of this each panel. So let's imagine this is the situation. You want to, for example, if you want to analyze a flow over this kind of body. This is called airfoil. Okay. The flow is incoming, go over it, just like so. I want to analyze the flow field around this airfoil. So what if you are going to pick up a 3D source of panels? So this is a panel. Since this is panel, each one of them create the flow like this. Okay. It's kind of difficult to draw, but so this is a panel, source panel. So what if I'm going to pick up this one and use many of those source panels. Each one of those source panel is just a flat panel. Okay? So I'm using 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 of flat panels combined together to represent kind of shape like this. It's an airfoil made up by panel. So each one of them are straight panels making up airfoil. Okay. So in my particular case, I'm using only 13, but suppose if you use 100 panels of small tiny segment, each segment is straight. But if you use 100 panels, it's going to be a fairly smooth surface that actually fairly closely represent airfoil shape like this. Okay? So this is the body created by source panel, and each one of those panels create the velocity like this. Okay. Oh, good. The next step is, okay, what if I want to superimpose, I'm saying mathematically, superimposing series of panels against incoming uniform flow with magnitude b infinity and mathematically superimpose. What is the result? You are simulating the flow over airfoil. Okay, so that is the baseline idea of source panel method. Let's take a look at the next page. Okay. So as you can see, mathematically you can represent the two-dimensional body by using a series of panels. Now, this is the centroid of each straight panel called control point. At this control point, you are going to cancel out incoming velocities perpendicular direction component using each panel's induced velocity. So that means each control point of the panel, velocity perpendicular to the surface becomes 0. That actually force this surface on each panel become stagnation stream. Okay, so that is the basic idea of source panel method. That actually represents the flow over two-dimensional body like this. Okay, so let's move on to the next page. So this is how the panel is set up. Okay, so in this case, actually, you are using a small segment of straight panels. Panel 1, 2, 3, 4, ij panel. So total m number of panels. You can use any number of panels. Okay. At each panel, you are choosing centroid of each panel location is called control points. So control points, you are going to cancel out velocities b infinities perpendicular component perpendicular to the surface, which is equal and opposite to the velocity induced by this particular panel. So you are going to adjust the strengths of each panel, which is lambda, and then find out distribution of the strengths of each panel. And then that actually determines the CP, pressure coefficient, at each control surface, control point. Okay? So you are going to determine at each control point, which is centroid of each panel, the pressure coefficient distribution over the surface. Okay? So I'm going to skip the mathematical details here, and then let's move into the example problem. Okay. So this is the example problem. I'm going to kind of give you a demonstration using my own source panel code, which is made up in MATLAB. Okay. So let's take a look at the example problem here. There is a theoretical airfoil called a Joukowsky airfoil. The shape of this airfoil can be obtained from a circle originally by a mathematical transformation between two domains. Okay? It's something called conformal mapping, which is above and beyond of this class's scope, so we're not going to cover that. But there's a technique called conformal mapping, which actually transforms original one domain circular cross-section is going to be transformed into airfoil shape by using transformation equations. Okay. All right. Since this airfoil is a theoretically derived shape, originally circular cross-section, okay, the surface pressure coefficient distribution can also be obtained theoretically. In other words, CP distribution of originally circular cross-section is given. That is, using this equation transformed into the shape of airfoil. So analytical value of CP can also be transformed into. So you know that theoretical value. So let's using the source panel method, let's calculate the pressure coefficient distribution of symmetric Joukowsky airfoil at the angle of attack 0 degrees. And then let's compare that against theoretical value. Okay. So let me show you the home page. So if you click on the tools page, it is going to take you to the tools page. Now in here, you can see fundamental source panel code FSPC. Let's click on that. Okay, so this is the fundamental source panel code demonstrator made up by me. Okay, so you can download two things: airfoil data, MATLAB code, and then if you run it, you can get output data. So it's just airfoil data. Let's save it to desktop, and then this is a MATLAB.m file. Let's save it to desktop. Okay. Then I'm going to run MATLAB. Okay, it may take some time to come up with MATLAB. Okay, here we go. So here's MATLAB. Okay. Now, let me change the file location to desktop. Then let's open up AF data.txt. Let's open up. Okay, here we go. So this is AF data.txt. Okay. So here's a number of data points, total 40 data points. And at each data point, you are given so 3 data sets you can see. So this is a coordinate data set, X and Y, for panel location. So I'm using total 40 panels to represent this Joukowsky airfoil. And then this one represents the theoretical CP distribution for each panel. Okay. So anyway, let's just try to run it. Alright. I'm going to double click this one. And I'm going to run it. Okay. As soon as I run this fspc.m MATLAB code, it is going to ask you to type in A or A angle over text. I'm going to type in 0. Okay? If I do that, it is going to give you 2 sets of plots. Figure number 1, let's take a look. This figure number 1 shows you the location of panel's control point. So like I said, I'm using total 40 panels. So those are the location of panel control points where I compute the CP. Okay? So total 40 panels representing Joukowsky theoretical airfoil shape. Okay? So each panel seems to be, this is the one panel, the other panel, the other panel, the other panel. So this is a control point of each panel. That's where I compute CP. No, actually, sorry, I made a mistake. Sorry, those are the location of left and right of the panel, each panel. So this is one panel, this is another panel, this is another panel. So if you draw a straight line between those 2 points, that is one panel. If you draw a straight line between those two neighboring points, that's another panel. Control point of each panel is, of course, in the middle between those two data points. That's where I compute the CP. Sorry about that. Okay, so this is angle of attack 0. Okay? This is a symmetrical cross-section. So I'm going to only compute CP on top surface only. Okay? So that is the CP on top surface. Okay? So obviously, those are the data points of CP calculation that corresponds to in between those two. So this is one panel. Each panel comes with one control point where I compute CP. Okay? So this is the data points of CP of upper surface of the airfoil. Okay? This blue line represents the theoretical value which is given from originally circular cross-section transformed into this shape. So this blue line is a theoretical computation of CP distribution. So this is a zero angle of attack as you take a look at it. It seems to be fairly good. Fairly good matching between theory to panel method. Right? This is the theoretical value. These are the computed value at each panel control point, the CP value. Okay? So not so bad, huh? However, let's just repeat the same thing. Let's run FSPC again. Now this time, let's see, angle of attack 2 degrees. So this is the case that the angle of attack is 2 degrees. So it looks like slightly pitched up cross section. So those are again straight line drawn between those two data points, those are each panel representing this cross section. Once again, I'm going to compute CP distribution and product. Okay? Then immediately you notice something beginning to happen here. Oh. What's going on? I'm not sure what's going on. Seems to me you have a CP distribution. Right here is 0.18 to 0.58-ish. Then all of a sudden drop the pressure. So pressure goes up and drop down. Pressure goes up and drop down. Okay. Why that kind of thing happens here? We begin what? Well, how about I'm going to do angle of attack higher value, like 5 degrees. Here we go. So this is angle of attack 5 degrees, pitched up quite a bit. Then if I compute CP distribution using source panel methods. Okay. It's gonna be, whoa, really high value. Oh. Now, keep that in mind. I'm talking about only upper surface pressure coefficient. Okay, upper surface pressure coefficient. Right here, the pressure really increased. Really increased so that it is actually almost close to CP equal to 1. So what's CP equal to 1? What CP equal to 1 really is stagnation point, is it? Am I going to create the stagnation point here? What's going on? Well, all right. This is what's going on. Okay, let's see if I can find. taught something like that before. I think unit B4, B3, something like that. Okay. So remember unit B4, page 6. This is what you're seeing, okay? Source panel method. Basically, the source panel method does not constrain the amount of circulation within the flow field. Amount of circulation within the flow field is computed purely by the shape added together with incoming uniform flow. It is going to determine circulation based on the shape and angle of attack. So that is going to arbitrarily determine two stagnation points on the surface, such as we observed in flow of a circular cylinder with certain amount of spin. Okay. Location of two stagnation points over the flow over the surface depends only on one thing. What is it? How much spin do you have, which is circulation. Okay. So this is not invalid solution. This is mathematically correct because nothing constrains the amount of circulation here. So that's what you're seeing. So what you are seeing here is as you pitch up and pitch up and pitch up more, flow goes around, circulate here, creating temporary stagnation point. Okay? Whoa, that's not good. Because is it going to really happen in reality, in nature? So what you're seeing here is the solution just like this. Okay? Yeah, that's exactly what you're seeing. Can you see both? Okay. Can you see both? All right, good. So if you have a stagnation point formed up here, of course, yeah, you're going to have a really high pressure point formed up because stagnation point Cp equals 1. Okay? This is not good. This is not good. Remember in unit B4, is there any way to prevent this kind of thing? Let's go back again. So unit B4, we recognize this is not right, even though this is, mathematically speaking, not invalid solution. This is more or less reality. So what nature does is, it is going to adjust this one, right? It is going to adjust this one to a little bit lower value so that excess amount of vorticity is going to be shared, then establish smooth flow at the trailing edge. That is called starting vortex shedding, and then we can enforce using critical condition. Okay. Problem of source panel method. You cannot enforce critical condition. Okay? In order to enforce the cutter condition, either you create at the trailing edge the stagnation point, or you can adjust the flow here and here, making it equal to each other. Either way is fine, But there's no way in source panel method to do that. The reason here is, let's go back to here, this picture. Okay? The reason here is the only thing you can adjust in panel method is the magnitude of each panel's velocity. Okay? Even if you adjust each panel's velocity, you cannot prevent having the velocity perpendicular to this panel at the trailing edge versus velocity perpendicular to this panel at the trailing edge is equal to each other. You can never adjust such a thing. Okay? You can only adjust to see if the velocity perpendicular direction is 0, velocity perpendicular direction is 0, just about any panel. That's the only thing you can do. You can never mechanically, it's not mechanically because you're talking about mathematics. Mathematically speaking, it is impossible to enforce the condition for source panel method. Well, that's why people really don't use source panel method. Okay? So let's go back and close this MATLAB code. Okay? All right. So this example problem demonstrates clearly that source panel method has some fundamental issues. This is actually very, very fundamental issue. However, source panel method is really good to explain how the panel method works. So let's go back a few slides and take a look at, okay. So this basic idea is good. If you create each panel using source panel and then adjust the magnitude of each panel so that velocity perpendicular to each panel's control point is equal to 0, so that the surface of this body becomes stagnation streamline surface. Okay. So idea here is rather than using source panel to represent 2D or 3D surface, why don't we use a different kind of panel? Wow. What about vortex panel? That is the introduction to vortex panel method. So let's take a look. Okay, vortex panel method is very similar to, remember, point vortex. Point vortex. Let's take a look at it. So this is called point vortex. Okay. So this one also induced the velocity. And then let's think about line of vortex. So this is the line created by point vortex, series of point vortex lined up in a line. And then of course you can create the panel of vortex, right? It's kind of hard to draw a picture like that, but this kind of thing. So this is a point vortex, line vortex, panel of vortex. Each one of those panels can be used. Small tiny surface of each straight panel is going to be used up to represent the curved surface, of course. So this is a straight segment for each. But if you use lots of small tiny panels in the series, you can represent curved surface, okay, fairly accurately. So again, the rest of them is the same concept. Suppose if you use a series of vortex panels. This one is a source panel, so it's kind of essentially the same thing. You are going to represent vehicle's surface using source panel. Okay? Okay. Now, source panel also induce the velocity at the control point. So depending on the magnitude of each panel, you are going to create the velocity. Now, this velocity is going to be equal and opposite to the component of this B infinity's perpendicular component. Then you're going to cancel out the velocity perpendicular to each panel. So you're going to force the surface of this body become stagnation streamline surface. Okay? So stagnation streamline means that flow hits the streamline hits the stagnation point and then flow over the surface and flow away. Remember, stagnation streamline defines the solid body of the surface in ideal flow. So it's very, very similar to the source panel method. The purpose is trying to create the stagnation streamline to define the solid body surface. Okay. So let's take a look. So this is the vortex panel method. So you're going to use a series of straight panels to represent the 2D body and then superimpose against incoming uniform flow. Then attach the boundary condition for each control panel's control point. You're going to cancel out the velocity which is perpendicular direction to each panel so that each panel becomes surface of the stagnation streamline. Okay. So this is called vortex panel method. We do have a simplified version of vortex panel method which is called thin airfoil. Thin airfoil is you are going to choose mean camber line. Mean camber line is usually curved path if you have a camber. So suppose if this is a mean camber line, you are going to use these vortex panels, a series of vortex panels to represent the mean camber line. Then you are going to superimpose this mean camber line against incoming free stream. Okay. Then you are going to create stagnation streamline on top and bottom surface of this mean camber line. So you are going to purposefully ignore the thickness of the 2D body. So that's why it's called thin airfoil. It is going to fairly accurately represent aerodynamic phenomena if you ignore the thickness of the airfoil. So it works fine for thin airfoil. But if airfoil is fairly thick, of course you're going to introduce errors. Okay? Alright. So next page. Are you seeing it? Okay. So next page. Why vortex panel method is chosen over source panel method? This page gives you the answer. Vortex panel method can enforce the Coulter condition. How? Well, this is the 2D cross section that you want to represent by using series of panels. Take a look at the location of trailing edge. So this is a trailing edge. So trailing edge is formed up by those two panels. This panel and that panel, creating the trailing edge closure. Okay? Suppose if the magnitude of this panel, which is circulation per unit length of that. How about magnitude of this panel, which is also circulation, which is equal and opposite to each other. Okay? Then you're going to cancel the circulation at the trailing edge. So right here is trailing edge. This is a panel I. This is a panel I-1. Okay? So suppose this panel has this much circulation. Suppose this panel has equal and opposite circulation. So they're actually making that circulation gamma at the trailing edge is equal to 0. No circulation at the trailing edge. If there's no circulation at the trailing edge, of course, the velocity here, velocity there, departs smoothly at the trailing edge because there's no circulation in either way, this way or that way. This is good condition. So using vortex panel method, you can actually enforce the Coulter condition at the trailing edge so that you are going to avoid flow curling up this direction or flow curling up to that direction, creating temporary stagnation point here or there, which makes the flow field really weird, right? Flow field looks like this. Usually this will never happen in nature. The reason here is the circulation amount is going to be adjusted so that the flow is going to depart very smoothly at the trailing edge instead. This is called Coulter condition. You can apply this Coulter condition mathematically for this vortex panel method. Okay? Alright, next page. Vortex panel method code comes with variety, and then there are two different kinds. One is a first order code, the other one is second order code. We are going to employ first order code, which is first order code is at each panel you are going to have a circulation uniform. So this panel comes with this much uniform circulation. This panel comes with different circulation. This panel comes with different circulation. That's called the first order code. In order to use the first order code accurately, you need to probably have a little bit more larger amount of number of panels, okay, in order for accuracy. We can have a second order code. Second order code is something like this. Each panel, at the connecting point of each panel, you are going to have a common amount of circulation. So within those two values, from left to right of each panel, you are going to change the amount of circulation linearly. So smoothly connect up the distribution of circulation over the surface. This is going to complicate the code. So code structure is more difficult. However, if you can only afford to use small number of panels, such as 10, 20, 30, that's the only panel you use, this is going to provide you fairly accurate results, even though you're using small number of panels. If you choose to use first order code, you are going to probably need a little bit more than 10 panels, maybe 20, 30, 40, 50, maybe 100 panels. You need more panels in order to minimize the errors. Okay? So we have a variety of code. Now, the vortex panel code we're going to employ is Virginia Tech JavaScript. Okay. The reason why I'm using it is because when I was a graduate student at Virginia Tech, I was involved on this JavaScript quite a bit, so I'm kind of familiarized myself to it. So that's why I'm kind of using it. But this is essentially first order code. So first order code really means each panel comes with constant circulation. So you have a distinctive jump at each panel's connecting point. Okay. All right. So this is one example of vortex panel application for NACA 0012 airfoil. NACA 0012 is maximum thickness 12% of the code symmetric airfoil. At alpha equal to 9 degrees, fairly high angle of attack, you're going to compute the CP distribution on top surface and bottom surface, and then plot it and compare against experimental results, I believe. Upper surface, lower surface, which matches up really well. Okay. So, all right. So let me just demonstrate you the vortex panel method. This is the job applet provided by Virginia Tech website. Okay. So using Virginia Tech vortex panel method job applet, let's determine the lift coefficient of NACA 0009 airfoil over a range of angle of attack 0 to 16 degrees. Plot a lift curve CO versus alpha and compare it against the NACA airfoil bed. Okay, that's good. So there are a few stages to do this. Let me just do it. So click here, takes you to the Virginia Tech job applet homepage. Looks like it. Okay, here we go. So now you're going to click on the vortex panel method. Then you launch it. So this is a vortex panel job applet. Okay. So what you need to do is you're going to provide your airfoil coordinate data, which is essentially the panels. So let's just show you a demo. If you just click on compute button here without any data, this applet automatically load up NACA 0012 standard coordinate data here. Now, if you want to run NACA 0009 airfoil or any other NACA airfoil, you have to first of all come up with the airfoil coordinate data. That's this one. Let me tell you the important thing, airfoil coordinate data. Okay, so this job applet takes the coordinate data just like this. This is X over C. This is Y over C. Let's be very careful. This is X over C. Y over C. Okay. This is a NACA 0012, so airfoil coordinate data probably looks like this. X over C equals to 0 means leading edge. X over C1 is a trailing edge. Okay? So as you look at this, it starts from 1 and 0, right? Starts with 1 and 0, which is right here. This is the starting point. So the data set need to start from trailing edge. This is the trailing edge. Okay? Then as you take a close look at it, this is going to be gradually reducing It's a decreasing number. Can you zoom in a little bit? Really good. Can you zoom in really good? Just to show the numbers. Okay? Zoom in. Alright. Zoom in here. Show the number. Very good. Okay. So starting from 1 and 0, this is the trailing edge. Then if you scroll down, the data starts from 1 and go all the way to 0. Then here, these are all minus values to 0. Okay. So data flows like this. Starting from trailing edge, going over the lower surface, so what you're seeing is lower surface data, right? Then here, take a look, zoom in. Then you see 0 and 0. Okay, are you seeing it? Okay, 0 and 0. What is 0 and 0? This is really leading edge. That means you're seeing here. 0 and 0 is leading edge. Alright. Let's go back here again. Zoom really into the value. So what are you seeing here? Well, starting from 0 and 0, leading edge, numbers are increasing to 1. Those are positive values. What do you mean by that? Let's go here. This is what you're seeing. Starting from leading edge, go to trailing edge. This is upper surface data, right? Upper surface data. So what you're seeing is from here upper surface data. Then ended up in 1 and 0. Okay? So let's zoom out and show this picture, please. Everything. Are you seeing everything here? So keep in mind, you create the data set of airfoil coordinate just like this. This is the flow of data starting from 1 and 0. Represent the lower surface data, and 0, 0 is the leading edge. Then go upper surface data and finish up at 1, 0. This is the complete airfoil coordinate data. Then after you complete this one, you are going to cut and paste into here. Then you're ready to compute. Okay? So let's just sorry about that. Let's just click compute here. Are you seeing compute buttons also? Zoom out a little bit, show everything. You need to zoom out a little bit, show all the screen. Okay? Alright. So after you cut and paste all your X and Y data here, you are going to click compute. If you do that, based on the X and Y data, coordinate set data, you are going to create the panel locations. Okay? And then these represent control point. At each control point, you're going to compute the CP data on top and bottom surface. This is upper surface, this is lower surface. This is the case of angle of attack 8 degrees. So if you pitch up 8 degrees, you are going to create CP distribution upper lower surface like this. And then, of course, the area bounded by upper and lower surface, this area, represents the amount of lift coefficient. So you can compute the lift coefficient, in this case 0.95. Okay? So you can change the angle of attack. Please zoom in here. Show the numbers. Okay? So now I'm going to type in 0. Are you seeing 0? Are you? Okay? If you type in 0 and click compute, are you seeing compute? And then let's now zoom back and take a look at CP distribution here. This is a 0 angle of attack. CP on upper surface, CP lower surface is about the same. As a result, lift coefficient 0. This is a symmetric airfoil. So at the 0 angle of attack, you don't create any lift. Okay? Alright. So now, let me just demonstrate to you the real thing. Okay. Let me just minimize. So, okay. Alright, so let's remember unit C1. Please show the screen, entire screen. Okay. Remember, there's a website, NACA 4-digit, 5-digit generator. So let's just take a look at NACA 4-digit generator website. Click on it and visit. Okay. All right. So this is a NACA 4-digit series profile generator. Okay. Please, can you zoom in a little bit and show this one? All right. Okay. All right. So what I want is NACA 0009. Of course, you can create any 4-digit NACA. This is the thickness. So no, it's not thickness. Thickness is this. This is NACA 0011, 0010, 009, 008, 76. So you can change the thickness. Of course, you can change the maximum camber and maximum camber location. Okay? So suppose if you put more camber, and you can change around the maximum camber location too. So you can play with it, but what I want is NACA 0009. So no camber, maximum thickness, 9% of the code. So this is NACA 0009 symmetric airfoil. Are you showing it? Okay. So what I want is a coordinate data. So how many data you want? 100, yeah, 100 is fine. So let's just click here, show points. So it is going to create the data sets here. So I'm going to pick up all the data set, 100 data sets, and then Control-C copy. Then what I'm going to do is, let me just create maybe text document. Open up, Control-V paste. So this is just an airfoil coordinate data. NACA 0009. This is 100 data coordinate data, 100 data sets. This is X over C, this is Y over C. So I have to do a little bit of modification here. First of all, I don't need a title, so I need to remove title. Then it looks like this one doesn't have a trailing edge. there's no point 1 and 0. So I'm going to type in 1 and 0. So I just manually created trailing edge here. Then if you look at that, going down, looks like 0 and 0 shows up here. This is the leading edge. Then as you go down, this is, okay, looks like 1 and minus that very small value. So this is 1 and 0. So I'm going to replace this one with 1 and 0. Okay? Good. Then I'm going to save this one on the desktop, number 009. Okay? Alright, so this is NACA 009 data set. So the next step is I want to open this one using Microsoft Excel because I want to do some manipulation of the data set. So I'm going to open up Microsoft Excel first. Okay, so I will open up Microsoft Excel. Then using Microsoft Excel, I'm going to open this data. So File, open desktop file, which is all files. Then as you can see, this one, open. Now Microsoft Excel starts asking a few questions. Then they are aware that you have 2 columns of data. These are the same thing or are these different? So I'm saying it's different. It is going to be delimited using a space. Okay? So I'm going to choose delimited, then click next. Then I'm going to click on space. So that means now Microsoft Excel recognizes this one is a single set of data, this is another set of data. Okay? Then click finish. Run. Alright, so now this is the data set all imported into Microsoft Excel. Okay. Well, we still have a problem. What kind of problem is that? Let's take a closer look at the data structure here. This is 1 and 0 trailing edge. These are positive values. So this from here to location 00, which is leading edge. Location 00 is leading edge. So this chunk is upper surface data. This is a leading edge. This is a minus value, so this chunk is lower surface data. Let's come here. So the data set I incorporated here. Starts from here, go upper surface, and then go lower surface. That's the data structure. You have to reverse it. Starting from here, data need to flow from trailing edge to leading edge, then leading edge to trailing edge. So you have to arrange the data sets like this. Can we do such a thing? Yes, we can in using Excel. So let's go back to Excel. Okay. So I'm going to somehow reverse the order rather than data running from top surface, lower surface. I want to have a data set lower surface first and then top surface. What is the best way? Well, can I completely reverse the order? Yes, I can. So let's do that, just to keep showing the screen, okay? So first of all, I'm going to insert a row, insert here. So this is essentially index. So I'm going to index these data. This is 1, this is equal to whatever this cell plus 1. Then I'm going to copy this to the rest of the cell, all the way down to 199. I paste it. So now I made up an index. Okay, just to zoom in a little bit more. So these are just the index. So those are the numbers made up by equations, so I don't like it. So insert once again. Oops. Then I'm going to copy, then paste number only values. Then I'm going to delete the original data sets. So now this is just a number 1 to 200. It's just index. Okay. So 1 to 199, 199 data set, just indexed out. So using this index, I'm going to completely debus this data sets. Rather than going from here to there, I'm going to completely flip-flop it. How can I do that? I'm going to choose this A, then sort and filter. Sort largest to smallest, then expand the selection. That's it, right? Oops. Sorry. For some reason this one needs to be all the way to the bottom. Sorry about that. It's another training edge, 1 and 0. Okay. Then I don't need this index anymore. Delete. Here we go. So this is now data set starting from trailing edge. This is lower surface all the way to leading edge. Then once you hit the leading edge, you're showing upper surface. Go all the way to trailing edge again. So let's turn in. Now your data is going to be arranged like this, starting from leading edge, lower surface to, starting from trailing edge, lower surface data to leading edge, and then upper surface data back to trailing edge. So this kind of arrangement. Is that right? Okay. Now you are ready. Now you are ready to go. So this is NACA 0009 coordinate data. You're going to use this coordinate data for your panel locations. So you're going to go back to vortex panel method. So you're going to delete. Okay. So you are going to select all of those data set. Looks like 199 data points. Okay. Control copy, and then you're going to paste it here. Control B, here we go. So now you copied and pasted your coordinate data from trailing edge to leading edge to trailing edge, lower surface first and upper surface. Then you're ready to go. Click compute. Do you see everything? Click compute. All right, now, so this is the new shape, which is NACA 0009 you imported here. And then as you specify your angle of attack, you can compute CP distribution, and then based on the CP distribution difference from lower and upper surface, you are going to determine lift coefficient. Okay, so now I do have 199 data points. So as you look, wow, there are lots of data. And then I can see there are a few funny locations, especially closer to the trailing edge. So you have a too much cluster of panels, especially near the trailing edge, so I would probably say I don't need this data point. I delete it. Okay, I'm going to retain trailing edge, but right next to it, it's such a small tiny distance, so I'm going to delete it. I don't need that. Then I'm going to go all the way down right next to the bottom surface, actually top surface, deleting this point. Can you zoom really in to show the numbers? Okay, what I'm doing is I'm going to highlight, looks like right next to the trailing edge. I don't need this data point, so I'm going to remove it. Okay? And let's compute again. Oh, I still have a few more points. I'm going to remove those two. And I'm going to go all the way up. I'm going to remove those two also. Compute. Yeah, okay. Still a few more. I probably don't need this one either. Compute. Alright. So pay special attention very close to the trailing edge. If you have way too many small tiny panels clustered up here, it is going to create the jumpy data points, which is error. Okay? So let's just start it to pitching up and pitching down and to see what happens. So what about 5 degrees alpha? I'm going to type in 5 here, then click compute. So 5 degrees alpha, you're going to show the difference between upper surface, lower surface CP. So obviously the area bounded by those two curves is going to be lift coefficient, CL. So if you pitch up more, like 9 degrees, you're going to create more pressure difference between upper surface, lower surface. Obviously, bigger area leads to larger lift coefficient. Okay? So you can use this software and then pitch up and pitch down and plot CL against alpha. That is essentially lift curve slope. So what you can do is you can pitch up and pitch down using that software. This is a symmetric airfoil, so you're going to probably end up having this kind of plot. Okay? This is a lift curve. You can do the same thing for cambered airfoil. If you have a positive cambered airfoil, it is going to be like that, shifted to left. If you have a negative cambered airfoil, it is going to be like this, shifted to the right. Okay? Then you are going to come up with alpha, zero lift. This is alpha, zero lift, right here. This is alpha, zero lift for negative camber. So you can use this software, vortex panel method, to compute lift curve, which is very, very useful information for your design airplane cross sections. Okay, airfoil. So the best way to run the tool is to basically pick it up and do it by yourself. So this is going to be your semester project, team project. So you're going to use this software to analyze the potential flow field. Okay. All right, let's stop here.